Sorry, we had some Wi-Fi issues here, so sorry for the delay. My name is Sohail. I'm going to talk about Openflow and virtualization, just an overview. If we have time, I will show you a demo and like a brief hands-on experience of what is Openflow. So traditionally, networking gears have the mainframe business model. So you have a big box. That this box has forwarding hardware. On top of that, there is operating system. There are a lot of apps. And on top of that, you have a management interface that you can connect to this switch, router, or any kind of networking gear. Configure that using this app to just get a network functionality out of a single box. So basically, these apps in the switches that can be hardware accelerated or not, or just software only, are implementing more than 5,000 RFCs, which means like hundreds of protocols and tens of protocol families, which in an enterprise you will use just a handful of them. But these switches, because they have to sell it off the shelf, you buy it and you can use different features, different protocols. The network gear provider has to implement these, like routing, access control protocols, and many other transport protocols and security things like IGP, BGP routing protocols, and lots of them. So these boxes are actually becoming the SUVs of networks. So they're, if you will, they're low-tech. As you can see in this figure, there's a software here that is customized for this hardware. So basically, we have very strongly coupled hardware and software. And packets are mostly processed here. But this hardware is controlled by these applications here. So we have data and control things strongly coupled as well. And there's no open API actually before Openflow. So when Openflow emerged, network providers started to provide APIs and SDKs. So we are living in a better world now, but it's kind of too late because Openflow is targeting this open API, lack of open API. So that three major problem result into complex, rigid, and expensive boxes. So this box have, if you want to buy it, you have to pay for all the apps that they have developed and all the hardware that you might not use. And because you don't have open API, you have to pay operational costs, which are high. So basically, if you watch the talks of networking people, like James Hamilton from Amazon, which is a senior staff there, the argument is essentially network is always in your way. Because these boxes here are really bloated, they're hard to manage, and they are the SUVs. So when cloud and virtualization emerged, instead of just one end-host in the data center, you have several VMs. Like on Hadi's laptop, you've seen 2 VMs. Like he could host more than that. And these VMs, each of them, like my VMs, would be hosted with yours. And they have to provide isolation costs, QoS, SLAs, lots of other security stuff, just to provide an illusion that these 2 VMs are running on a LAN. And it is really hard because networking gears do not provide good management APIs. So the community started to ask for open APIs for the switches. So there's a single API that you can use for configuring the switch. In the research community, network operators and network programmers all need an open API. So in the research community, they started to develop that API. And there's actually a background for that, like it has been started in 90s. But Openflow has started in 2006, so there's a history there. But they were all aiming at providing an API. So the first question is here, when you want to create an API, is what are the functionalities, right? So what are the functionalities that you want to expose outside that box? So basically, we are looking for network primitives, right? So what are the network primitives? There are things that are done in data plane. Everything that is done in like hardware in the silicon chip that you can buy off the shelf is providing those primitives, right? So like forwarding a packet from one port of a switch to another port, writing the header of the packet, implementing TCL, something like that, adding a VLAN tag to a packet. These are all primitives of network that are provided, they can be easily provided in hardware. So they assume that data plane functionalities, these simple functions, are the primitives, and then they, based on that primitives that are inside our forwarding layer, they provide an API, which is called Openflow API. And that's basically exposing the primitives supported like in hardware, and then you can access it in software and configure the box, configure this forwarding or data plane here. Does that make sense? So it's really simple, but the problem is we have many traditional network boxes in our network, and it's really hard to make them OpenFlow enabled and then build a software that controls that switch. So an OpenFlow network usually consists of networking gears that are OpenFlow enabled, and that software is called the network controller that provides an abstraction of the network. This is like a middleware, like say Apache server for your apps, for networking apps, that provide these APIs. That I will show you a demo of those apps, a simple demo. But the basic thing is there is a TCP connection here, and then controller talks to the switch, and your app using the network controller can configure the network element. Comparing this to traditional network gear, anything beyond the operating system of the networking gear is actually moved to the software. So these two are decoupled in OpenFlow network. So you have a software controlling those boxes, and you have hardware and OSes running on these networking gears that are just doing forwarding and data plane that are performing those data plane and forwarding functions. In the literature, this portion of the network is called data plane, and anything beyond the controller is called control plane, your apps and the controllers. And that's why the argument behind OpenFlow is decoupling data plane from control plane. So in traditional network gear, you have control plane and data plane in a single box, and now you have decoupled them. Your boxes run, and they're centrally controlled. Just in brief, I will get into details of each of these items, but what OpenFlow provides is a handshaking. An OpenFlow switch can handshake with a controller, like, hello, I'm the switch, I have these features, I have these many ports. And controller also can do some handshaking stuff. You can check the status of the ports and the switch, collecting the stats. And also you can install forwarding rules. And what is a flow entry rules? These are flow entries. So that one is the input port, this column. This is the source MAC address, destination MAC address, source IP, destination IP, TCP source port, TCP destination port. And this is the action you want to apply. So these are the flow entry rules. These are the main part of OpenFlow. So what the first rule says is any packet coming from switch port number 1 forward it to port number 2. And any packet that is its destination port is 4444, drop it. Or any packet coming from port 1 with this wide-carded MAC address and with this IP prefix, forward it to port number 3. That is this simple. So Openflow gives you the API to install these kind of rules on the switch. So, but there is a problem in this flowing switch rate. And what's the problem? There's a conflict between these two. So it's not that simple. So when you're installing rules, you have to take care of conflicts. And okay, when a packet comes, and any packet that matches this row will match that row as well. So what I can do with this? So there are many details inside the Openflow's protocol and specification, which are beyond this presentation, but it is not that easy to configure the network. So you have to take care of these complexities in software. So Openflow is a boss in network virtualization domain. So network virtualization is always referred to as a killer app for Openflow. So it's the best fit for Openflow. Why? Because in that network that I've shown you that we have several virtual machines, we need a programmable control interface for the switches. We require easier management that Openflow provides for us. You can automatically configure it in software. And it is vendor agnostic, so Amazon can buy Openflow switches that are conformant to that standard and use it out of the box in its network, using the software that was controlling another switch, but using the Openflow API. And that is important for warehouse scale data centers. So let me give you an example of network virtualization in Openflow. Suppose that we have this simple network, and we have OpenStack, our cloud controller, like Nova in OpenStack, over there. We have an Openflow controller that controls our switches, and we have two Openflow-enabled switch. And your machines are connected to those switches, and that Openflow controller controls that switch. Let's say we have the blue tenant, our blue user. The first request is create a VM for me. So create VM goes to this cloud controller, and this cloud controller first boots the VM using any technologies they're using. So there's a VM booted here. Then it tells the Openflow controller that my VM is hosted on Hadi's laptop. There's an interface attached to it. And attach this VM to user B's network. Okay. So Openflow controllers know there's a VM on one of the machines connected to switch 1. And it knows this link is connected to port 1 of this switch. Okay. So it tells the switch to tag any packet coming from this port with blue, color that with blue. It can be implemented as VLAN or MPLS or anything. So that switch, after Openflow tells the switch, has a forwarding rule that if the port is number 1, color the packet as blue. Let's say another request comes from that user, putting VM2. The same process happens, and another rule is installed here. So any packet coming from port 1 is marked as blue, and from port 2 is marked as blue, and from port 1 marked as blue. Let's say another user requested his first VM in the purple network. What happens here is adding another rule to that switch, right? Anything coming from port 3, color it with purple. Then another VM, it requests another VM, and that VM, because the host connected to the switch are full, we have to put it on another switch. And the Openflow controller tells switch 2 that each packet coming from port 1 with purple. So what it does is installing another rule. So right now our network has the state of 4 rules on 2 switches. If you wanted to do this with traditional network, you have to create this whole Openflow thing on your own, like using their command line interface or buying some SDK from them to do this. But Openflow provides an open API that you can do this with any Openflow switch. That one can come from Cisco, the other one can come from Juniper, if they support Openflow. So let's say this user starts to ping VM2 from its VM1. What happens is a packet is generated on the interface of this VM, right? So it goes to the first switch. It's marked as purple because there is a rule here that says if the packet comes from port 3, just color it as purple, and it forwards it to another switch. And what happens here? What did we do here? We matched this packet with these 3 rules. So that packet was coming from port 3, so we matched this rule and we applied this action, right? So what should happen here? We should go over the rules, right? So there is a rule called, that rule, the first rule from, if a packet comes from port number 1, color it purple. Does this packet come from port 1? So what happens? You can drop it, or by default, the switch forwards this packet to the controller. Okay? So when there's no match, you can configure this, either drop it or send it to the controller. But by default, it's sent to the controller. The controller then decides that, okay, this packet is purple. Probably it should be forwarded to port 1, which is for the connected to VM2. So it installs another rule on the switch, which is if the packet is purple, send it on port number 1. So in this example, we have 2 types of rule installation. We have proactively installed 4 rules when the VMs were booting off, and we have reactively as a reaction to a packet, a new packet which doesn't match any rule, we install another rule on that switch. So in Openflow networks, when you want to design networks, there are 2 approaches. You can install all the rules reactively or proactively, or a hybrid, which I've done here. What is the problem with reactive? It's actually will make your network slower because every packet has to go to the controller. They have to do some computation, install the rules. So there's at least a flow initiation delay. But if you install all the packets, all the rules proactively, your network won't have any flow initiation delay, but you can have a dynamic network that based on the load and number of the packets installing new rules, right? So you have to monitor. It's basically a trade-off between programmability and performance. And this is basically what is done in OpenStack with Openflow today. So they have the quantum here that tells the Openflow controller that I have these switches and this VM is connected to this switch, it's booted up, connect this interface to this switch, and we have blue networks and purple networks. So they have IDs for the network, and instead of colors, you just have numbers. So this is roughly what is happening there. And this process that we were talking about is called network embedding. So the network embedding problem, which is the theoretical aspect of network virtualization, you have a request for virtual networks, like user blue has requested 2 VMs that are connected, or purple, 2 VMs that are connected. And then you want the cloud computing infrastructure to map it to its physical network. So this is what is done using Openflow and OpenStack.
There's a question.
Sure.
How does Openflow differentiate between users?
In this example, for example. So Openflow does not know the user. It just when the cloud controller adds a user, for each user we have, say, a network with a unique ID. Each user can have multiple networks in OpenStack, for example. But let's say I have network 1 and you have network 2. So for each VM that is booted up for network 1, there's a driver here that boots up your virtual interface. And that virtual interface is part of, in OpenStack, is part of Nova, for example. It's mostly part of the virtualization library you use. After you initiate that interface, this Nova network manager tells the Openflow controller that we have a network and the interface is ready. So what it does is assigning a rule that push a VLAN tag on that interface for any outcoming packet.
Through VLAN ID, differentiate between different rules.
In one implementation. In another, you can use MPLS. Okay. There is actually some implementations that don't use any tag. So basically, because you have in OpenStack-like environments that you have control over the MAC addresses of these interfaces, you can assign any MAC address you want, right? So, and if that MAC address is unique in your network, you can use it as for forwarding groups on the first switch, and then but you have to keep that MAC address on the packet when it arrives at the destination. So a harder version of that embedding problem is when the user requests a virtual switch. So in Solly, for example, you will have a network experimenter that just a researcher that wants a networking experiment running on Solly. That network experiment have an Openflow switch between 2 VMs. So in this case, it is actually much harder than what we have seen in the previous example, that you have to boot these VMs and then just install root. You have to provide a virtual switch, and that virtual switch provides a connectivity. So it looks really complex, but with Openflow, it's actually easy to realize and embed this virtual network. So let's say we have this green network here. You boot up the VM on this end host, VM2 on this end host, and you want to allocate this virtual switch on this physical switch. So there was a virtual host on a physical host. There's a virtual switch on a physical switch. But how does it happen? So any rule that this controller of the researcher is going to install on his virtual switch, you are going to AND it with tag green. So it can just affect packets that are labeled as green. So any packet that is inside network green, they will go through the rules installed with that control. Okay. And any packet that is green and is not matched to any rule in this switch is forwarded to that control. So basically, this controller sees this can connect to this switch, but only for the green network. So it has a slice of the network. You tag each packet on these interfaces, and in between in the network, you can just use that tag for virtualization. Does that make sense? So it's basically a very simple slicing based on labels. Rules are and the green, and all matched green packets are sent to this controller. So this was just an overview. So a little bit more details in Openflow. So how they actually implement Openflow in switches? Because there is no market just for Openflow only switches for now, they have to compile Openflow agents under switches that SUV just has an API, an agent that's providing that API. So basically today Openflow switches are not Openflow only. They are hybrid. They are traditional switches that have Openflow here. So the first goal is not achieved yet. So the switches are not cheap. They are still expensive. They're bloated. And because this Openflow agent is running on their operating system, there are many things, there are many complexities here, like how they reply to the rules. If you install a rule on a switch, you can't be sure that that rule is actually in hardware. It might take 4 seconds for that operating system to install, depending on the switch. And there are switches that will take that will apply a rule in microseconds. So you have different switches because of the complexities of the traditional box. They can't provide an IDOM, an Openflow agent on the switch. So today it's not as good as I presented in the previous example. There is a software switch called OpenV switch. It is first started by people working on Openflow, and it's upstream in Linux 3.3, so it's available. The kernel module is there, and all the switches most of the switches that are Openflow enabled off the shelf are actually using OpenV switch, and it's just compile it on their own switches. So it's very portable to hardware, and like what Pronto does is just compiling that OBS on their switch. That is the Openflow agent on display. So another problem that you've not asked is how do we configure that Openflow switch and tell where is the controller to connect to? So there's a chicken and egg problem, right? You have the switch, but if you connect it to the network, how does it find the controller? Or how controller can register itself inside the switch? So after a while, just this year, there is an Openflow config standard that is released for solving that problem. Previously, you had to connect to that switch using CLI and configure it when you buy it and connect it to the network, tell where is the controller. And that was the one-time configuration on all Openflow switches. So it's not that simple to deploy Openflow switches. You have to configure them to for where is the Openflow controller, what is the IP, and what is the port. In Openflow config, there is a controller assignment, so you can cluster your controllers, which is really good. So you can failovers that if this controller crashes, connect to this controller instead. And you can also configure ports like port up and down using the Openflow config. So what are the cons of Openflow? First of all, there is a scalability issue. You have a fully distributed system. Each box we're operating on its own. Well, you have to configure that, but let's say they're fully distributed. And we are moving all the brain in these switches to a central location. So we are actually centralizing that. So there is a scalability problem here. So to solve that problem, there are lots of distributed control planes, like on-X hyperflow, give-off-flow, and can-do, which is my research. And these controllers are really fast. So, for example, can-do can handle 1.4 million packets on a commodity Xeon server on a single core with a single thread. So they are actually scalable, but we have to admit that there are scalability problems in Openflow. In Openflow 1.2, they have master-slave controller using that Openflow config that I was talking about. And when you're going with reactive model, you have the scalability problems. But when you go with proactive model, because you install the rules proactively, There is not much communication between the switch and the controller. So you just use that API to configure the switch. You push the configuration, and that's it. So there's not much scalability problem when you use proactive model. And in industry, all the deployments are using proactive model. So there's no reactive deployment, to the best of my knowledge.
Very nice. So in terms of scalability, you still have your controller has to have a network view, right? Of the entire topology of your network and all the flows. Would that not be a scalability issue?
Well, for the proactive model?
Yeah, even for proactive.
The topology is just for when the switch comes up, it's a handshake, right? And for topology discovery, they're using LLDP protocol. So it's actually less than what is done on today network. So in today network, if you want to discover the topology, you have to run discovery mechanism on each of the switches. So you have n squared messages. But in Openflow, you have 2n because each switch only talks to the controller.
Yeah, but still, I think you're mainly considering like a LAN environment, but
oh yes,
if it goes to LAN,
so
multiple LAN.
Openflow is suited for data centers and LAN. It's not well suited for internet scale networks. It is basically like for SABI, you have nodes. Those nodes are Openflow enabled. And within the nodes, you have macro Openflow management, right? Because there are not much switches involved. But when you talk about the whole Ethernet, you can't have a single Openflow controller that controls the whole big network.
Sure, there's no no concept of abstraction of a LAN with like hundreds of switches to see that as one unit, or somehow to be able to manage this capability.
Well, in Onyx, they provide an abstraction that you can say, okay, I have a complicated factory topology, and just give me a mesh of this network. So they provide an abstraction on top of that. But
what's it called?
Onyx.
Yeah, what's the name of that abstraction?
It is called network interfaces, information-based, like wrapped information-based network. It's NIP. So, but that is actually more scalable than other no abstraction controllers because you can have hierarchies of abstractions. So you create a network, compress it in like one object on a controller, and there's a controller on top that just controls, has a very general overall view of this network. So there's no detailed information about what is the flows are managed in the lower layer.
Yeah, but you still might have flows between networks, between abstractions.
Yes.
Which you still need a unique tag.
Unique tag problem in a data center?
Or if you deploy one virtual machine in Asia, one in North America, you have physically different networks, right?
If you don't have control over the interconnection between these two networks, like if you don't have a VPN, a tunnel, or something that your tag does not draw, there's actually much of practical problems there. That you have to send this packet, and if you have control over that you can have an abstract tunnel which represents a virtual link between two networks. There is no scalability problem. Probably there are performance problems, but
probably there are two controllers involved.
There's actually a hierarchy of controllers. So in Onyx, Hyperflow, DevOpsflow, and Can Do, there's a hierarchy of controllers. So for example, in Can Do, we have two layers of control. One of them does this simple task that are previously done on the switch directly. The application that doesn't need to know the whole network, doesn't need to have the whole network view. And you handle frequent events here. So if you want to have like a hub application or learning switch app, you run it here because that learning switch app doesn't need to know anything about these switches. And then any RAID event, like a switch join, a port is down, a port is off, goes to the higher controller that needs to have the network-wide view for routing protocols and stuff. So basically, without a hierarchical without hierarchical scheme, you can't deploy it in a WAN. But if you have a hierarchical set of controllers, you can deploy new maps. That's actually what Google is doing. So this can-do is one of the distributed controllers that will actually make your network orders of magnitude more scalable. So it doesn't let the frequent networking events like a packet comes or statistic collections go up to the root controller. So you will have for each, for a handful of switches, you will have a local controller that is fast and just do very simple stuff. And just rare events are propagated to the higher layer. So you can scale this way. So there's an efficiency problem that we have low setup latency if you go with reactive model. And that latency can be really high. I will show you in a demo. It can be 2 orders of magnitude higher than a normal set. And the other problem, which is much important than scalability, but it's not really, for now, it's not the focus of controller vendors, is consistency. The problem is you have a network at time t, and at time t prime, there's another network. Like a switch has gone down. So you have to reconfigure the switches. And then when you want to install version 2 of your rules, the second configuration, if there was a packet on the fly matching those old rules, and then you install a new rule, and that packet that was actually supposed to be forwarded using old rules, in the middle of its way started to getting influenced by the new flow. So there is a consistency problem. It might be even a route loop there. That it's actually, after the real-world deployment, scalability is not that much of a concern now. Consistency is the real problem there. When you have everything centralized, and you have to take care of versionings of the rule. So this is like for Google, they could scale for G-scale, but they had to take care of consistency issues. If there is a talk in Open Network Summit just a few months ago, and this is like the focus of most of the talks there.